So is the PDF file visible to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay, so this is tutorial number 12, and in this one we will look at some questions on the topic of DFT and the properties of DFT. Especially, there are two properties that are important. One is linearity, and the other one is the circular shift. So we will look at these questions related to that. So okay, so let me start with the question number one. In this question, we have it is said that consider the sequence x of n, uh, and it is given by x of n is equal to alpha raised to the power n un, and we have to assume that mod of alpha is less than 1. Now, first of all, we obtain a periodic sequence x tilde n, right? So also in the lectures, the same notation is used for a periodic sequence. We say that x tilde of n is periodic. So the way we construct them is that we take x tilde n and we basically say that after r times n, this xn will repeat, and that is how using this expression we will obtain x tilde n, which is basically the periodic version of x of n. So x of n will be there on the left as well as on the right of the original sequence. So the first part is we simply have to find out the DTFT x e raised to the power j omega of x of n. And then in the second part, we have to determine the discrete Fourier series coefficients, that is this capital X tilde k for the sequence X tilde n, right? So let's first do the first two parts, and okay, let's look at the third question also. The third part says that we have to find out the relation between the two, right? So we have to find out the DTFT, the discrete Fourier series coefficients, and then we have to relate both of them. Okay, so let's look at the solution. So it goes like this. This is what is given to us. We have x of n, that is alpha raised to the power n un, mod of alpha less than 1. And also, how do we obtain x tilde n? We just say that it's a periodic version of x of n. Alpha is still less than 1, mod of alpha less than 1. So we have to first of all find out the DTFT. We all know the formula for DTFT by now. It is x e raised to the power j omega is summation is from minus infinity to infinity for n, and xn is multiplied with e raised to the power minus j omega n, right? So I substitute x of n as alpha raised to the power n, uh, also un, and when I compute this, it will be 1 by 1 minus uh, alpha, sorry, this is alpha times e raised to the power minus j omega, right? So that is what this will give us, and also obviously mod of alpha is less than 1, which is given to us, right? So this is simply the DTFT, which we have already seen previously. In calculating the DFS of x tilde n, what we say is that we have capital X tilde k, which is the discrete Fourier series coefficient. And how do we obtain this? We just take, now the summation is from 0 to n minus 1, because xn is periodic, and 0 to n minus 1 is contains all the sequences of the all the sequences. So because now it is finite time, and then we multiply it with this w n k n matrix. So if you remember from the lecture, this is nothing but e raised to the power minus j pi k n by capital N, right? This was the notation we used for that. Now we can substitute x tilde n here, which was given to us as x, this part. R is from minus infinity to infinity, x n plus Rn, right? This was given to us in the question. So I have substituted it here, and this is what the whole thing I'll get now, right? And now, what is xn? So xn was alpha raised to the power n un. So I can write down xn plus rn as alpha n. I replace n with n plus r capital N, and un with un plus r capital N. And because there is this un term here, a unit step term here, I can uh, um, absorb this term into the summation, and the summation will now be from 0 to infinity because un is a right sided sequence, and that gives us this one. Now I can take these terms into their respective summations. So n is equal to 0 to n minus 1. So this term alpha raised to the power n can be here, and this term also contains n. So I have taken alpha raised to the power n and this w, which also depends on n, in this summation, while on the outside I have taken the summation of r, and only one term is there that depends upon r, and that is alpha raised to the power r capital N. So I've written it like this. Now it's only about applying the formulas for these integrals, and this will be 1 minus this term raised to the power capital N, right? And on the denominator we will have 1 minus just this term, right? So yeah, so that's how we obtain. So basically, the in the numerator we have small n equals to capital N, and in the denominator we just have without the raised to the power small n. So this is what we'll get, right? And then obviously there is another summation, which is alpha r raised to the power n, and this is quite also straightforward. We'll get 1 by 1 minus a, sorry, alpha raised to the power n. So this is because of this summation, and this summation will result into this part, and we will finally get this expression where the mod of alpha less than 1. Then we can find out, we can say that x tilde k can be written as, so if you see that the denominator and the numerator are actually the same, because this e raised to the power minus j2 pi k will be equal to 1. So I can cancel the numerator and denominator. I'll be left with only this part in the denominator, and that's what this is, x tilde k. Right. So this was the second part where we calculated the discrete Fourier series coefficient. Now the third part says that we have to compare the DTFT and this DFS. So these are the two. I have written the results of the part A and part B. This is the DTFT, the first one, and the second one is the discrete Fourier series. And you can quite easily see that there is a simple relation that omega is replaced by 2 pi k by capital N. So what does that mean? That means that here we have we can write it like this: x tilde k is x e raised to the power j omega with omega substituted as 2 pi k by capital N. Or in other words, we can say that the frequency scaling that has occurred is like this, right? Because if you remember, when we are in DTFT, we are moving in the unit circle in the z plane, right? And basically we are scaling the unit circle by substituting this thing. Okay, so now coming to question number 2. Okay, so in this question we have been given by the way, if anybody has any question, you can interrupt me in between, no problem. Otherwise I'll move to this second part. So we have two 8-point sequences that are given to us, x1n and x2n, and these have been plotted in these two figures, and their corresponding discrete Fourier transforms are x1k and x2k respectively. We have to determine the relationship between their discrete Fourier transforms, right? So these are the two sequences. We have their corresponding discrete Fourier transforms as x1k and x2k, and we have to find out how their discrete Fourier transforms are related. So remember to approach such kind of questions. The best way is to first find out the relationship between x1n and x2n. So if you notice here, we have 8 points. This is A, B, C, D, E. These are the value of the magnitudes. And if you look in the second one, this is A, B, C, which is these three, and then D, E, which is here. And there are also these zeros which are here. So the relation is that in some way these two are related through the circular shift. So the circular shift, these are related through the circular shift property. That is the first thing that we notice. And we will utilize this observation to actually find out the relation between the discrete Fourier transforms. So let me go to the solution. Yeah. So as it says here that by observing x1n and x2n, it is clear that the two 8-point sequences are related through a circular shift, right? So how is the circular shift there? So if you see that A, which is in 1, goes to A here, which is at 5. So there is a shift of uh, uh, 4 indexes, right? From 1 we have gone to 5. So we can write this down like this. We say that x2n is obtained by x1 n minus 4 modulo 8, right? Because it is an 8-point sequence and the shift is of 4, right? So this is how we will represent this shift, right? And we remember we use this modulo sign because originally x1 is not periodic, but when we use this modulo sign, we are essentially thinking of it as a periodic sequence, because only then we can apply the circular shift. uh, or we can see the circular shift as a linear shift in that case, if we first of all make it periodic. So this is the expression for what is happening there, right? And so we say that if, let's say, x1n has the DFT of given by x1k, then we can say that this particular thing, x1 n minus 4 modulo 8, will have a DFT which will be given by this term. So we have introduced the e raised to the power minus j 2 pi times 4. So small n is 4 times k divided by capital N, which is 8. And this is how we represent that using this W. And so basically this shift will be multiplied for the discrete Fourier transform when we have this on the left hand side or on the uh, time domain. So this is what's happening, right? So that means basically that since this is nothing but x2n, so x2k, this would be x2k, right? And x2k is related to x1k by this relationship. Or in other words, we can solve this thing w4k 8, and this is basically this. So 8 from the numerator and denominator will cancel out, and this is nothing but e raised to the power minus j pi k, right? And I can say that x2k is basically e raised to the power minus j pi k times x1k, and this is nothing but this is minus 1 raised to the power k, right? So this will give me minus 1, but depending upon what k is, whether it's even or odd, we can write it like this, right? And this is the final relationship between the DFTs of x1 and x2. So we have utilized the circular shift property in order to find out this relationship. So are there any doubts so far?
No, sir.
Okay. Okay, so I'll move to question number 3, and this is the last question. This is a relatively small tutorial. So this is the last question for this tutorial, and so here we have been given two 4-point sequences, xn and hn, right? These are two 4-point sequences, which means that they are only non-zero for 4 indexes. N is from 0 to 3. One is xn is equal to cos pi n by 2, and second is hn equals to 2 raised to the power n. So let's first focus on the first two parts where it is said that we have to find out their discrete Fourier transform, right? So we have to find out the discrete Fourier transform of these two sequences. So first let's look at these two parts. Okay, so again I have written them down for you. The first one, this is the first one, x of n is equal to cos pi n by 2. N is varying from 0 to 3, right? So this is the first one, uh, and we have to find out its discrete Fourier transform, which is this x capital K, which is summation n is from 0 to 3 cos pi n by 2, right? So basically, when we calculate this discrete Fourier transform, we take sum from 0 to n minus 1, which is 3. And this is x of n, and then we have the term e raised to the power minus j pi kn by capital N, and capital N is 4, right? And this wkn by with a base of 4 is actually just a shorthand symbol to denote that complex exponential. And again, remember that both the sequence and its DFT have the same number of number of elements. So here also k is varying from 0 to 3, right? Okay, so we can solve this. We know that cos pi n by 2 will only be non-zero for once when we put n equals to 0, because then it will be cos 0, that's 1. And then also for cos, when I put n equals to 2, then it will become cos pi, which is minus 1. For cos 1 and cos, sorry, for n is equal to 1 and for n is equal to 3, this will become 0, right? So that means that the cosine term contributes only two non-zero values to the summation. And so that's why I can write this as, first of all, when we have cos 0, this will be 1, and this will be n equals to 0, which will also be 1. So we have 1, and then the second term will be for n equals to 2, this will be minus 1, so a negative sign, and this will be e raised to the power minus j pi k, right? Because uh, n equals to 2, and so uh, uh, yeah, actually there should be minus j pi k by 2 here, right? Because n is 2 and capital N is 4. So we will get minus j pi k by 2 here, right? Or the shorthand notation will be 1 minus w 2k, and here in the uh, uh, subscript there will be 4, right? This is the symbol. So this is xk, k from 0 to 3, right? So this was the first part, and in the second part we have been given hn, which is 2 raised to the power n, n varying from 0 to 3, right? And we have to find out again its DFT. So we will take summation from 0 to n minus 1. N minus 1 is 3. 2 raised to the power n times this notation for uh, complex exponential. So when we solve this, so first of all, uh, when I evaluate 2 raised to the power n at 0, 1, 2, and 3, I'll get 1, 2, 4, and 8 respectively. And for this W4KN, I have just written it. For n equals to 0, it is 1. For n equals to 1, I'll get this term, and then this term, and finally this term. So, or I can write it completely as the complex exponential that it is, right? So here small n is 1 and capital N is 4. So it just becomes e raised to the power minus j pi k by 4. And similarly with the other cases as well. So this is capital H of k, right? So now in the first and second parts, we have computed the xk and hk, which are the DFTs. Let's look at the third and fourth parts. So in the third part, we have been asked to compute this thing. This is yn, which is the circular convolution of xn and hn with n equals to 4, right? So whenever you see this symbol, this is with a number written inside it, this means circular convolution. So this is while this is not a topic that is I think it will be covered in the one of the lectures that is left. But this is a very simple topic and it's really quite easy to grasp. So in this question, what we have to do is we have to basically we know already how xn and hn will have their convolution. We can compute the convolution of xn and hn in the normal way, in the standard way. But this, on the other hand, is the symbol for a circular convolution. So we will see how to do this in the part C. Okay. So here comes part C. We have yn, which is xn circular convolution with hn. And the way you have to understand circular convolution is, if you haven't already studied it in signals and systems, you just remember that circular convolution is linear convolution plus aliasing. We've already seen linear convolution, I think in the second or third tutorial, or maybe in the first tutorial itself. So the only thing is that it will be linear convolution only, but there will be aliasing, right? So if we had to take the linear convolution, then what would have been the result of the length of the resulting sequence, right? So we have xn and hn. So if you see, both xn and hn were from 0, n going from 0 to 3, which means that capital N is equal to 4, right? There are 4 sequences. And the same was the case with this one as well, hn. It also had capital N equals to 4, right? So for linear convolution, we know that the length of the resulting sequence is n1 plus n2 minus 1, which will be 4 plus 4 minus 1, that is 7, right? If I take the linear convolution of xn and hn, I will get the resulting sequence having a length of 7. So the capital N for it will be 7. But on the other hand, because we are calculating circular convolution and it is saying that the length of the resulting sequence must be 4. So that is what this means. This means that the circular convolution is performed in a way that the non-zero number of sequences, or the number of indexes which have non-zero value are 4. So, and we have to remember that if we want to avoid aliasing in circular convolution, the condition is that capital N, which is the length of the resulting sequence, must be greater than or equal to 7, which is the length of this sequence, which is the maximum possible length which we obtain from linear convolution. So this is the condition. Now it is given to us that this capital N is actually 4. And that means that this condition is not true, and there will be aliasing when we do the circular convolution of xn and hn. And how much will the aliasing be? So it says that since capital N is 4, there will be an aliasing of 7 minus 4, that is the 3 points. Okay, so let us first find out through the regular way the convolution of xn and hn. If we would just take the convolution the way we have done it previously in the first or second tutorial, we would get yn as this sequence. Okay, so as you can see, there are 7 values that are non-zero, or where, or the values where there is something, right? So it is from 0 to 6. So n minus 1 is 6 or n is 7, right? So this is what would happen if I take the simple convolution. Now there will be aliasing, and because of aliasing, there will be the last 3 points will actually wrap around on the top of the first 3 points. That is what will happen as a result of the circular convolution, that these 3 points will overlap with the first 3 points, right? Because we saw that the aliasing will be of 3 points. Okay, so let's first of all see how we will compute this circular convolution. And this is actually quite straightforward. So first of all, what we will do is we have this x of n cos pi n by 2 0 to n minus 3, right? Sorry, n from 0 to 3, right? So first of all, let us write it in terms of this set where we put in the set the magnitudes of x of n. So all we have to do is we have to evaluate this function at n from 0 to 3. So at n equals to 0, it is 1, and then 0, then minus 1, and then again 0, right? Just evaluating this function at all the values of n, I get this set. I'll do the same thing with h of n as well. I have 2 raised to the power n. I will evaluate it at all the values and I will get this set, which is 1, 2, 4, and 8. Okay. And now, in order to take the circular convolution, we will use this method which is known as the matrix multiplication method, which is a very straightforward method. All you have to do is, so we have xn and hn. So what I'm going to do is I'm going to keep all the magnitudes of x of n in one column of this matrix. And then I'm going to shift these elements such that this x0 will come into this position, x1 will come into this position, and so on. So the last element was xn minus 1. It will move to the first place. Similarly, for the next column, I will again move x0 on the third place, x1 on the fourth place, xn minus 1 on the second place, this xn minus 2 on the first place. So we are just shifting each element by one and obtaining a new column until in the last row we have done it such that this x0 comes at the bottom, right? So that is how we will obtain this matrix. And this second vector is actually just the elements of h kept in a single vector in a column, right? So it will be just be h0 to hn minus 1. I will take this matrix vector multiplication, and this will give me some vector, and this vector will actually be the resulting sequence, which is obtained by circular convolution, right? So it is quite easy to understand the rationale behind this, because if essentially what we do in circular convolution is that we go back into the and multiply with the previous elements, and that is why we have this shifting vectors, and this is the result of the circular convolutions. There are other methods for computation of the circular convolution, such as the concentric circles method, but this one is probably the simplest, and I have given this one, right? So let us do this for xn and hn. And one thing that you will note also is that the dimension of this will be equal to capital N, which is also the dimension of both xn and hn, right? So which in this case will be 4. So let's take the product of xn and hn. I have taken 1 0 minus 1 and 0, put it as a first column. This is the first column which corresponds to the magnitudes of x of n. Then I will shift it once. 1 will come here, 0 will come here, minus 1 will come here, and this 0 will go up. And then I will obtain this matrix by this shifting. Then in the second vector, I have written down the elements of h of n. And when I take the product, I'll get this minus 3, minus 6, 3 and 6. And this is the resulting vector or the resulting sequence magnitudes when we take the circular convolution. So that means that when we find out this convolution yn, which is xn convolution with hn with the resulting sequence as 4, we will get this minus 3, minus 6, 3 and 6. So here it is minus 3, minus 6, 3 and 6. So this is what the resulting sequence is, and it is different from the sequence that we got by the simple convolution, right? And it is so we remember we said that circular convolution is nothing but linear convolution plus aliasing, and that you can note here as well. So if I take this sequence and if I take these 3 points and I overlap them with these 3 points, then I will get the circular convolution. Because if I, let's say, take the 4th one and add it to the first one, the first one is value 1 and this is minus 4, I'll get minus 3. In the second place, I will get 2 minus 8, which is minus 6, right? And this is 0, so no difference is made to this. So I'll get minus 3, minus 6, 3 and 6. And that is what you see here, minus 3, minus 6, 3 and 6, right? These are the magnitudes. And this is basically what circular convolution is. Okay, so with this, we have calculated the circular convolution. Now, coming to the last part of question 3, we have y of n. Now we have to find out y of n, not by this method, but by actually taking the DFTs of x of n and h of n and then multiplying them, right? Because circular convolution, here yn is the circular convolution. If I take the DFT, it will just be the multiplication of the DFT of xn and hn. And then I can take inverse DFT for the resulting yk to obtain this y of n. So this is the D. These are the sequences hk, xk and hk which were obtained from the part A and B, right? All we have to do is we have to find out y capital Yk by multiplying these two. I've just written down what we got from the part A and part B of this question, and then we multiply them together. So I will get this term here. Okay, and one thing to note here is that the term W4K4 is the same as W0K4, right? Because here we will have e raised to the power minus j pi k, and the same will be here, and both of these terms are actually equal to 1, right? We can use this thing, and also we can note that W5K4 is the same as WK4, right? You can again see, and this is obviously a result of the fact that we are moving around a unit circle, and if this is minus j pi k by 4, this will be minus j pi 5k by 4, right? So 5 pi by 4 and pi by 4, so they are the same for the powers of complex exponentials. And so we can substitute it here, and we will get, so there are a few terms like W4 4k, which is this term, which will become just minus 4. So minus 4 plus 1, which will give me this minus 3. Similarly, on substituting this one as well, I will get finally this expression. Okay, and this is for k going from 0 to 3. Now I have to find out y of n. So I just take the inverse DTFT. This will become minus 3 delta n and this term actually is nothing but the shift. So this will be delta n minus 1, because here small n is actually 1, or you can say n naught is actually 1, and here it will be delta n minus 2, and this will be delta n minus 3. And you see that the magnitudes are actually reflect that this is minus 3, this is minus 6, 3 and 6, just like we saw in the previous case. So we have again computed yn, but not by taking the circular convolution approach, but by taking the DFT and multiplying the uh, inputs and the impulse response. And this will be the final yn, n varying from 0 to 3. So this was the last question, and this was its last part. So with this, the tutorial 12 is over. And are there any doubts?
No, sir.
No, sir.
Okay. This could also be the last tutorial. So if you have any doubts in general or anything to discuss, this is the time. Or so, are there no doubts at all? Everything is clear?
Yes, sir. Ev- Everything is clear for now.
Okay. Rohan has also, I guess, again rejoined. So, well, the tutorial is over. I was just asking if anyone has any doubts. So, Rohan, anything to add?
No, sir. Thank you. It was nice.
Okay. So, yeah, these are the questions, generally the type of questions that you can be asked from DFT. It's a quite a simple topic, and you can practice these kinds of question only. And yeah, so this is probably the last tutorial. So thank you. It was great to teach you all.
Excuse me, sir.
Uh, yeah, yes, Priyanshu.
It's Rohan.
Sorry, Rohan. Yes.
Sir, can you suggest the book that we should follow for this particular subject? I mean, is Oppenheim enough?
Yeah, I think for all the concepts, Oppenheim is enough, because most of the times for making these tutorials, as well as making the even the lectures, we follow Oppenheim only. So yeah, it's quite. I think it's sufficient to follow one book only.
Okay, okay. Thank you.
Okay, so I guess then, if there are no more questions, we can end this tutorial. Thank you, everyone. All the best.
Thank you, sir.
Thank you, sir.
Thank you.